Assalamualaikum warahmatullahi wabarakatuh. I am Khairul Adahani binti Karuniza. My matrix ID is MA18102. I will be explaining, I am from Pahang. Today I will explain the chapter 1 of experiment 2. Okay, boundary layer is first discovered by Ludwig Prand in the early 1900. He said that as object move through a fluid or the other way around, it will disturb the particles around the object. The particles right next to the surface will stick to it, and the collision of the particles above the surface with the particles that stick to the surface will slow down the particles around the objects. These particles will slow down the flow above them. And a thin layer of fluid is developed near the surface in which the velocity changes from zero at the surface of object to the free stream value away from the surface. This phenomenon is called as boundary layer. And in this boundary layer, aerodynamic forces are generated between the fluid and the object. The main forces in the aerodynamic are drag force and lift force. As the fluid flows through an object, a resistant force will prevent the object from moving to its direction. This resistant force is the drag force. Okay. The drag force remains constant either the object moves through the fluid or fluid flows past the object, as the relative motion remains the same. If the object flow through the fluid has an angle, the drag force won't be the only force that existed. There will be horizontal and vertical forces. The horizontal force is the drag force and the vertical force is the lift force. The lift force is perpendicular to the flow of direction. This is the weight region. This is the weight region where the stagnation pressure is larger compared to zero angle of attack. The dividing streamline and the stagnation point move down, so more air flows above the wing. Therefore, there will be a decrease in velocity below the aerofoil. As you know, the Bernoulli's theorem stated that the velocity decrease, the pressure will increase. So the pressure below the aerofoil is higher than the pressure above the aerofoil. This is how the lift force is generated. This is the formula for coefficient of drag force and coefficient of lift force. These are the problem statements. First, evaluate the flow patterns of the immersed bodies and the boundary layer theory. Second, calculate the velocity, height, pressure, viscosity of fluid near solid boundary and add symmetric aerofoil at different angle of attack. Lastly, measure the flow rate at different type of surfaces of the flat plate. These are the objectives of the experiment. First, to design complete measurement technique for fluid flow and measure the drag and lift forces applied on a symmetrical aerofoil at different angles of attack. Secondly, to determine the velocity distribution for flat plate. Lastly, to determine the boundary layer thickness of a flat plate subjected to longitudinal flow for rough and smooth surface. These are the scopes of the experiment. The usage of multi-tube manometer in readings to obtain static head measurement and liquid height. The usage of pitot tube inside the flow air bench and the usage of calipers on the right side of flow air bench after setting the value to zero angle to measure the velocity of the fluid flow on the plate surface. Lastly, calculate the estimation of drag force and lift force at different shapes of object and surface roughness and angle of attack. I will pass the next slide to my friends. Thank you.
Hello and Assalamualaikum. My name is Muhammad Hafiz Adnin bin Zaharuddin. My metric number is MA18081 and I'm currently living in Kuantan, Pahang. For this video, I'm going to talk about the theories part. So for flow over immersed bodies, the resultant of pressure and shear forces for two-dimensional flows, infinitely long and of constant cross-sectional size and shape can be resolved into two components, which is one in the flow direction and the other in the flow normal direction, which is the drag force and lift force. And this figure below shows an aerofoil where it contains the lift force and drag force. So for drag force, the drag force is the force that a flowing fluid exerts on a body in the flow direction, and the magnitude of this force is influenced by viscosity, a fluid stream's force on any obstacle in its path, or the force felt by an object moving through a fluid. Designers of moving vehicles, ships, suspension bridges, cooling towers, and other structures must consider its magnitude and how it can be reduced. Traditionally, drag forces are described by a drag coefficient, which is defined regardless of the shape of the body. The sum of friction and pressure drag is the total drag force. Shearing stresses acting on the body surface as a result of velocity deformation cause friction drag. The force due to friction drag is calculated by integrating the shear stress across the body surface, whereas the force due to pressure drag is calculated by integrating the forces due to static pressure across the object's surface. In streamlined objects like an aerofoil, friction drag is the most significant contributor to drag, whereas pressure drag is the most significant contributor to drag in blunt objects like plate. The formula for drag force is as below. So for lift force, a force is exerted on an object by a fluid flowing around its surface. The component of this force that is perpendicular to the direction of oncoming flows is called lift. The drag force, on the other hand, is the component of the force that is parallel to the flow direction. Lift is usually applied in an upward direction to counteract gravity, but it can be applied in any direction at right angles to the flow. As for an example, in Bernoulli's theorem, where decrease in velocity, pressure will increase. Therefore, the pressure below the aerofoil is higher than the pressure above the aerofoil. The lift is generated in this way. As shown below is the formula for lift force and lift coefficient. So for boundary layer over a flat plate, in the same way that flow is in duct can be laminar or turbulent, so can flow in boundary layer. In boundary layer, there is no single value of the Reynolds number at which the transition from laminar to turbulent flows occur. Pressure gradient, surface roughness, heat transfer, body forces, and free stream disturbance are all factors that influence boundary layer transition. A boundary layer forms over a long, essentially flat surface in many real-world flow situations. Figure below show a qualitative representation of boundary layer growth on a flat plate. That portion of fluid flow near a solid surface where shear stresses are significant and the inviscid flow assumption may not be used. All solid surfaces interact with viscous fluid flow because of the no-slip condition, a physical requirement that a fluid and solid have equal velocities at their interface. Thus, a fluid flow is retarded by a fixed solid surface and a finite slow-moving boundary layer is formed. A requirement for the boundary layer to be thin is that the Reynolds number of the body be large, 103 or more. Under this condition, the flow outside the boundary layer is essentially inviscid and plays the role of a driving mechanism for the layer. That is all from me. Thank you.
Assalamualaikum and very good morning to everyone. My name is Muhammad Amir Azmin. Today I will explain about chapter 3 method and procedure for lab report 2. This lab report has two experiments which is experiment 1 is flow pattern of symmetric airfoil at different angle of attack, and the second experiment is flow over flat plate. First, I will discuss about experiment 1, flow pattern of symmetric airfoil at different angle of attack. First, the experiment setup is shown in the figure 1, just like in this figure. And then, the second step is airfoil mode is attached and screwed to the airflow bench. And then the first angle attack 0 degree is selected to start the experiment. And then the switch is turned on. The smoke control is pressed to emit smoke. This is smoke in the figure 2. And then the radar fan is allowed to move. The picture of the flow is taken. The reading is recorded and tabulated. And then the radar fan speed contour is increased. And lastly, the experiment is repeated for angle of attack of 30 degree, 45 degree, and 60 degree. Next, for experiment 2, flow over flat plate. First step is the experiment is set up as shown in the figure 3. And then the smooth surface flat plate is inserted into the airflow bench. The distance of 10 mm is taken at first value. And then the pitot tube is connected to the vernier caliper. Step 5 is the pitot tube is first touched to the surface of the flat plate at the first data. And then the radar fan is turned on and any data are recorded and tabulated. And next is the distance of the plate is increased by 10 mm to 30 mm. And then while the pitot tube distance from the surface of the flat plate is increased by 2 mm to 6 mm. And lastly, the experiment is repeated for the raw surface. I think that's all for chapter 3 for method and procedure. Thank you very much.
Assalamualaikum warahmatullahi wabarakatuh. My name is Wan Muhammad Razima Rushdam bin Muhammad Rashid. Metric ID MA18114. Today I will discuss the result for this experiment. For experiment 1, flow pattern on symmetric aerofoil at different angle of attack at 3 different angle of attack of 0, 30 and 45. We can see that when the speed is increased, the force also increase. Next, experiment 2, flow over flat plate. From the graph above demonstrate that when the thickness of the boundary layer increase, the manometer height decrease. This is because a thicker boundary layer causes the pressure in fluid flows from the pitot tube to rise, pushing the fluid into manometer and lowering the manometer's height reading. From the graph above, show that when the thickness of boundary layer increase, the velocity increase. This is related to the viscosity of the fluid, which permit it to stick to the surface due to the non-slip boundary condition. From the graph indicates that as the thickness of boundary layer increase, so does the Reynolds number. The higher the fluid velocity, the greater the Reynolds number according to the Reynolds number equation. We may deduce from the graph and table that Reynolds number increase proportional to the plate distance. From the graph, we can see that the graph indicates that as the distance of plate increase, so does the velocity. Further discussion is observed in the first experiment. Air may flow in a variety of patterns over various surfaces. By manipulating the fluid flow at various angles, we were able to determine the lift and drag force of an aerofoil at each angle. The experiment started with 3 different attack angles, 0 degrees, 30 degrees and 45 degrees. We observed that when a rough surface is compared to smooth surface, the rough surface had a thicker border layer in the second experiment. In other words, the rough surface will have lower fluid and Reynolds numbers due to the high viscosity effect. The smooth surface has greater Reynolds number than the rough surface. Thus, as the velocity rises, the flow becomes more turbulent. Lastly, for the conclusion, we may conclude from the first experiment, which include flow over an immersed body, that 3 most critical elements that determine the streamline profile are the angle of the immersed body relative to the y direction, the shape of immersed body, and y speed. As a result, engineer and designer in today's world are working to lower the Reynolds number in order to lessen the amount of energy used when driving an automobile. Because drag force is related to Reynolds number, a high Reynolds number will result in more drag. However, we may conclude from experimental boundary layers that some variables such as fluid flow speed, Reynolds number, plate roughness, and others influence the boundary layer on the plate. We can see that velocity is proportional to the Reynolds number from the equation of the Reynolds number